All right, this is section 3.5, summary of curve sketching. All right, so this is not necessarily the order in which you should do things, right? This is not the order in which you should do things, like domain. It's helpful, but not necessarily do first. Range. In fact, this says complete last. Okay. X-intercepts. These are help. This X-intercept is helpful. Y-intercept is helpful because it's a specific point. Symmetry, I don't even care if you answer that question. All right. Horizontal asymptotes. Horizontal asymptote is important. This helps you shape the graph very much. Vertical asymptotes are important. So if you do anything, you should really do 3, 4, 6, and 7. First derivative analysis, it's helpful. Second derivative analysis, that's helpful. And then graph them. First, you draw the asymptotes. Plot all the points found from the above investigation. So when it says above investigation, that's x-intercept, y-intercept. First derivative analysis should give you maxes and mins, right? And you should get a point of inflection out of the second derivative, all right? Then graph it, right? Then graph it. All right, so I'm going to do example one from that's on page 198. It's page 198 of the Incredibles book, page 198. All right, so I'm going to zoom in a little bit. Now, I'm going to try to do it in the order given, but except for the range. When they do suggest that you do the range for last. Let me zoom in a little bit. So you don't have to, whatever. All right, so here's my function, x squared over x squared minus 16. The domain, the easiest way to determine the domain is say what it cannot be. So this is a fraction, so the denominator cannot be 0. So what will make the denominator equal to 0? Plus or minus 4. So the domain is all real numbers, but plus or minus 4. So I just say x is not equal to plus or minus 4. This implies it could be anything else. Right? You don't have to say what it is. You can give it an answer in interval notation, or you could just tell it like that. Range, like I said, we're going to save that for last. X-intercept, that's when the function's equal to 0. So you're going to solve this equation, f of x equals 0. Right? I shouldn't have written it there. That will be the work, not the answer, right? So in fact, I'm going to scratch that out and find the work. So I'm going to do the work for that. So that we're doing x squared over x squared minus 16 equals 0. Right? We're doing x squared over x squared minus 16 equals 0. So that means for a fraction equals 0, only the numerator equals 0. So that means x equals 0. Okay? So that's the answer. So the x-intercept is at x equals 0. Okay? That's the x-intercept. It crosses at the x equals 0. Which is also, now what's the y-intercept? So y-intercept is you're looking for, so this was x-intercept over here, right? When we set the function equal to 0, and then when we get the y-intercept, all we're going to do is find what is f of 0. F of 0 would be 0 squared over 0 squared minus 16, which is just 0. All right? So that's the y-intercept. So it turns out the x-intercept and the y-intercept are the same, so it's 0, 0. And you can put the order pair here, 0, 0. So both of them, x-intercept is 0, 0, y-intercept is 0, 0. Symmetry, like I said, I don't really care. Horizontal asymptotes. So you should be able to look at the function to see what the horizontal asymptote is. You look at the degrees are the same, so it's just a coefficient of those highest degrees. So it's 1 over 1. So we have a horizontal asymptote at y equals 1. Vertical asymptote is when the denominator is equal to 0 and it doesn't cancel with the numerator. So that'll be x equals plus or minus 4. So x equals plus or minus 4. That's the vertical asymptotes. Then find the derivative. So what I want to do is take the derivative on the back of the paper, and then I'm going to write it over here. So the function is x over x squared minus 16. Right? F of x equals x squared over x squared minus 16. All right, so now I'm going to take the derivative. So f prime of x equals, so bring up the denominator times the derivative of the numerator minus derivative of the denominator times the numerator over x squared minus 16 squared. Okay, go ahead and clean that up. So I'm just going to multiply out the numerator. So it'll be 2x times x squared is 2x cubed minus 32x minus 2x cubed over x squared minus 16 squared. All right, and then Simplify that. So that's going to be the 2x cubes cancel. So it's negative 32x over x squared minus 16 squared. So that is the first derivative. I'll write that over here. Negative 32x. So f prime of x equals negative 32x over x squared minus 16 squared. All right. Critical numbers. So critical numbers, you set this function equal to 0, and I'm going to get x equals 0. So that's a critical number. The denominator is undefined at x equals plus or minus 4, but that's not in the domain. So plus or minus 4 are not critical numbers. All right. However, when we make a sign chart, we have to use those points of discontinuity in our sign chart. Okay. So let's just plug in numbers. So if you plug in negative 5, that's going to make the numerator positive, right? Negative 5 times negative 32 is a positive number. Plug in negative 2, same effect. It's going to be a positive number. And you might be asking, well, why aren't you doing anything with the denominator? Well, the denominator is being squared, so it's always positive. So the sign of this derivative only comes from the numerator. If I plug in a positive number, it's going to be negative, right? Like 1 times negative 32 is negative. So it's negative on this side, and you'll see that it's negative. So go ahead and test it yourself. It turns out to be negative here. So this is one of those crazy ones where it doesn't alternate. So, be careful with that. All right. Now, so this is going to be our analysis here. Where is the function increasing? It's increasing from negative infinity to negative 4, and from negative 4 to 0. Now, some people say, well, why can't we just put it all together? Because we do have a major break at x equals negative 4. So you cannot just say negative infinity to 0, okay? Because there is a major break at negative 4, right? It's not continuous at negative 4. If it were continuous at negative 4, you could probably get away with rewriting it at just negative infinity to 0. But since it's not continuous at negative 4, you have to make that break. It's decreasing from 0 to 4 and from 4 to infinity, right? Because of this break. And if you're not sure what I'm talking about when I say break, when I graph it, you'll see what I'm talking about. Is there a relative minimum? No, right? There's only one sign chain, and it's at x equals 0, and it is continuous at x equals 0, so that is a max or a min. It goes from positive to negative, so that means it's going up and then down. So the relative minimum, there are none, so there's no relative minimum. There is a max at 0, 0, right? 0, because of the sign change of the derivative, and it's continuous at x equals 0. And if you plug it in, you get 0, right? We had 0, 0 already. All right. I'm going to copy the first derivative here to do my second derivative analysis. So first derivative, I'm just copying it here for reference. You don't have to copy it here because it's just right up there. Second derivative, so take the second derivative of that. So I'm going to do that on the back of my paper, or not, because I've run out of space already. All right, so I'm going to do, so the second derivative is, well, let me copy the first derivative first. Negative 32x over x squared minus 16 squared. So the second derivative is, bring up the denominator, so it's x squared minus 16 squared times the derivative of the numerator, right? The numerator is negative 32x, the derivative is negative 32, minus the derivative of the denominator, so that's going to be 2, bring on the exponent, I'm doing chain rule, x squared minus 16 times the derivative of the inside, which is 2x, times the numerator, which is negative 32x, all over x squared minus 16 to the 4th power. Right? We're going to raise it to the 4th power. All right, now continuing with this. Oh, it's kind of crooked. All right. Okay, I'm running out of space, so I've got to cover up the first derivative. Okay. So now we're going to, what are we doing? I don't know. Let's clean that up a little bit. I am going to factor out x squared minus 16 out of those two. There's a common factor of x squared minus 16 to both. So I'm going to take out the x squared minus 16. That's going to leave me, so there's an exponent of 2, so that means there's a single exponent. So it's going to be x squared minus 16 times the negative 32 minus, I'm taking the x squared minus 16 out, so that's going to leave a 2, a 2x, and a negative 3 to 2x. All right, that's all that. All that over x squared minus 16 to the fourth. So that means those two can reduce. The x squared minus 16 up front, x squared minus 16 to the fourth, that can reduce. This, so I'm going to reduce and simplify the numerator at the same time. This looks like 324, but it's 22x. Okay, so that's going to leave me x squared minus 16 times negative 32. So it's negative 32x squared plus 32 times 16. What is that? 32 times 2 is 64. Times 2 is 128. 256, 512. All right. Then here, minus, that makes it a plus. 2 times 2 is 4. 4 times 32, 64, 128. 128. X times x is x squared over. Remember, I reduced the x squared minus 16 with x squared minus 16 to the fourth in the denominator. So that becomes x squared minus 16 to the third. All right. Let's clean that up. So that's going to be 96x squared plus 512 over x squared minus 16 to the third. There we go. So that's my second derivative. All right, let's copy that to the front. That's 96x squared plus 512 over x squared minus 16 to the third power. All right, so that's the second derivative. What are the critical numbers of the second derivative? Well, the numerator, because it's something squared plus something, has no solution. So, and for a fraction that equals 0, you don't have to look at the numerator. Now, you could argue that it's undefined at plus or minus 4, but plus or minus 4 are not in the domain. So those aren't considered critical numbers. However, you still need to make them as part of your sign chart. So the only two numbers on the sign chart are those points of discontinuity, and negative 4 and positive 4. All right, so we're checking the second derivative. What's the sign of the second derivative on these intervals? So to the left of negative 4, say negative 5. The numerator is positive, right, because it's squared plus something, so it stays positive. So it's the denominator that can actually change the sign. You might be wondering, it didn't do it last time. Well, last time it was an even exponent. Now I have an odd exponent. If I have an odd exponent, if I have a negative number inside, it becomes negative. If a positive number inside, it's positive. So I'm going to plug in negative 5. Plug in negative 5 into this. That'll be positive 25. Minus 16 is 9. 9 to the third is positive. Plug in 0, right? 0 is between negative 4 and 4. Plug in 0. That becomes negative 16 to the third, which is a negative number. So it's negative. Plug in 5. Same effect as plugging in negative 5. It's going to be positive. If you're not sure about that, go ahead and do it yourself. All right? Concave up. Concave up, it's going to be between negative infinity and negative 4. It's concave, and more, between 4 and infinity. And it's concave down from negative 4 to 4. Now, it is changing concavity at x equals negative 4 and 4, but that was a break in the domain, so it's not considered a point of inflection, so you have no points of inflection. All right, now we're going to use this information to graph this puppy. All right, so first of all, I am going to use my x-intercept and y-intercept, so I have that. I'm going to use my horizontal asymptote. I have horizontal asymptote of y equals 1, so I'm going to do a dotted line there. I have vertical asymptote at plus or minus 4. 1, 2, 3, 4. So 1, 2, 3, 4. All right. It's increasing from negative infinity to negative 4, and then from negative 4 to 0. It's going to be increasing, so that means it's got to be going up. Okay. Let's look at something else. There's a max at 0, 0. So that means it's going up to there and down from there. And I want to confirm it's concave down. Right? Remember, it was concave down from negative 4 to 4, so that's okay. From negative infinity to negative 4, it's increasing. All right? And it is concave up. Right? It's concave up from negative infinity to negative 4. So it's going to look like this. And then it's also concave up from 4 to infinity. And don't forget, it's going towards that horizontal asymptote, y equals 1. So there it is. All right. Now, what was the range? Remember we said we're going to do the range last? And when we say last, we mean even after graphing it. All right. So the range is, it goes as high as 0, but then it breaks off until you hit 1. So the range is negative infinity to 0, and then 1 to positive infinity. So this is how low you go up to here, and then from 1 up. And notice I'm not including 1. I guess I do include the 0. All right. Ooh, so that's an error I did in class. All right. So that's the graph, and that's all my things. It is symmetrical to the y-axis, right? Symmetrical to symmetry to y-axis. If you're interested, all right, that's it. That is example 1.